In section 1.8, we're going to look at absolute value equations and inequalities. We start our discussion by talking about the definition of the absolute value of a number x, which we write as x enclosed in two vertical segments. It is defined as the distance from x to 0 on a number line. For example, if I were to say that the absolute value of x is equal to 5, that means that x is a number that is 5 units away from 0 on the number line. Well, x could certainly take on the value of 5 because 5 is a number that is 5 units from 0. So that could be one possible value of x. However, there's another possible value of x. What other number is 5 units from 0? Well, it's the number -5. So x could have two different values that meet this criteria. X could either be at +5, which is 5 units to the right of 0, or x could be at -5, which is also 5 units away from 0. This is why we can say that if the absolute value of some quantity capital X is equal to A, as long as A is a positive quantity, then that value, capital X, could live at either positive A or negative A, similar to what we just showed where A is 5. Now, note that here we're using a capital letter X to designate that X could be an algebraic expression, not just a single variable. For example, if we have that the absolute value of 9 times x is equal to 36, then 9 times x is serving as the algebraic expression capital X. Because 36 is positive, we can say that 9x is a quantity that is 36 units away from 0, either 36 units to the right or 36 units to the left at -36. This gives us two different equations to solve. In the first equation, by dividing both sides by 9, we get that x could be 4. In the second equation, dividing both sides by 9 gives us that x is equal to -4. That means that there are two solutions to this inequality, or absolute value equation, I should say, not inequality. The value 4 and the value -4 are both solutions. We use the curly brackets to designate a set. In our second example, we have that the absolute value of 4n minus 5 is equal to 6. Just like we did in our first example, we're going to say that the quantity 4n minus 5 is either 6 units to the right of 0, or 4n minus 5 is 6 units to the left of 0 at -6. The first equation looks like 4n equals 11 if we add 5 to both sides. Dividing both sides by 4 gives us that n is equal to 11/4. In the second equation, we have that 4 times n is equal to -1, and dividing both sides by 4 gives us that n is equal to -1/4. The two solutions for this absolute value equation are therefore 11/4 and -1/4. As I said in an earlier video, whenever you're writing the solution set as a list of solutions in these curly brackets, the order in which we list the solutions is not important. In our third example, we have that the absolute value of 9s plus 4, when we subtract 7 from that, we get the value -5. We're not ready to make the interpretation of distance just yet because the absolute value expression is not isolated. So let's add 7 to both sides first to isolate the absolute value quantity. -5 plus 7 gives us 2 on the right. That means that 9s plus 4 is a quantity that is 2 units away from 0. Either it is 2 units to the right of 0 at +2, or it is 2 units to the left of 0 at -2. The first equation becomes 9s is equal to -2 when we subtract 4 from both sides, or s is equal to -2/9. The second equation becomes 9s is equal to -6, or s is equal to -6/9, which reduces to -2/3. There are two solutions to this absolute value equation, and for the sake of space, I will let you write the solution set on your own using curly brackets. In the next two examples, we have more interesting algebraic expressions to work with. In number 4, we have 8 minus the absolute value of m plus 4 is equal to 1. The first thing I note is that the absolute value expression is not isolated. Because there's a negative sign in front of it, I'm going to add the absolute value of m plus 4 to both sides. So we'll have 8 equals 1 plus the absolute value of m plus 4. Then I'll subtract 1 to both sides to get that 7 is equal to the absolute value of m plus 4. Now that we have the absolute value expression isolated, we can make our distance interpretation. M plus 4 is a number that is 7 units away from 0, either 7 units to the right of 0 at 7, or it's 7 units to the left of 0 at -7. The first equation gives us that m is equal to 3 when we subtract 4 from both sides. The second equation gives us that m is equal to -11 when we subtract 4 from both sides. So the solution set here includes two values. M could either be +3 or m could be -11. In the next example, we might get the impression that there's a lot of work to be done. We see a polynomial inside the absolute value signs, and we're told that that expression is at a distance of -2 from 0. Well, already that should give us some pause. Can distance really be negative? Can this number live -2 units away from 0? Actually, that's nonsense. And so an expression like this, as interesting as it may be, gives us an equation that has no solution. The rationale here is that distance cannot be negative. So don't get carried away trying to follow a lot of mechanical steps when a simple pause to interpret what the absolute value is representing is going to save you a lot of trouble. Next, let's look at absolute value inequalities. If you understand that absolute value represents distance from 0 on the number line, then interpreting the absolute value as an inequality statement should be pretty simple. Here we have that if the absolute value of an algebraic expression capital X is strictly less than a, that means that the distance of that expression from 0 must be less than a. In other words, the values have to be close. For example, let's say that I have that the absolute value of x is less than 2. That means that x is a number that is less than 2 units away from 0. If we look at the number line, here is 0, here is 2, here is -2. Which numbers are less than 2 units away from 0, closer than 2 units away from 0? Certainly all of these and all of these, not 2, not -2, because we have to be closer than 2 units away. So we see that all the numbers that are between -2 and 2, without including -2 and 2, would be part of the solution set. So in other words, x must be greater than -2, but less than +2. Take a look at how this explanation ties to what we saw right here in this statement. In the second statement, we have that if the absolute value of an algebraic expression, capital X, is strictly greater than a, this is equivalent to saying that x must be less than -a or x must be strictly greater than a. Let's do an example to illustrate this as well. I'm going to do this in green to differentiate. So let's say, for instance, that the absolute value of some quantity x must be greater than 4. That means that x is a number that is more than 4 units from 0. Let's draw a number line and see where these values could fall. Here is 0, here is 4, here is -4. So we're looking for values that are more than 4 units away from 0. Well, certainly these over here are more than 4 units away from 0. They're further than 4 units away from 0. In fact, all of these would be. 4 would not be included, however. What other values are more than 4 units away from 0? Well, all of these over here as well. -4, though, would not be included. So we have two intervals of values that include values that are more than 4 units from 0. We have the left interval that has no lower limit, so we'll have -infinity as the lower boundary and -4 as our upper limit. And then we have the second interval, which goes from 4 with no upper limit. These are two separate intervals, and we're going to use the union symbol in between them to say that the values could be in either of these intervals. Another way of writing this is that either x is less than -4 or that x is strictly greater than 4, which again ties into what we just saw in the second statement. So again, by having absolute value represent distance from 0, saying that an absolute value expression is less than a units from 0 means that it has to be close to 0 within a units. But saying that the algebraic expression is more than a units away from 0 means that we're repelling it away from 0 and we're looking at numbers that are far away from 0 at more than a units away from 0. So that should kind of give you the visual that we're pushing away from 0 either to the left or to the right. I spent a lot of time talking about the interpretation because the mechanics are actually pretty simple as long as we understand the underlying concept. Let's take a look